Hello, everybody. Welcome back to another discussion in dynamics. Plan for today. We will just continue. We'll continue our momentum of particles, and today we will focus on direct impact and coefficient of restitution, and then we will just solve two examples. And besides that, I just want to say Happy Halloween. Okay, but before Halloween, unfortunately, discussion with me. So let's do that discussion, and then we can go and have fun. So I just wanna do brief lecture review. And I just want to focus on coefficient of restitution. Okay, so please imagine situation let's imagine two particles, okay? And let's imagine situation pre-impact. And of course, post-impact. So let's say that we have two particles. Let's say small one, and let's say big one, okay? And of course, this guy has to have velocity larger than this one, yeah? The guy on the left is chasing the guy on the right, yeah. And by the way, I think in your lecture notes, Professor Sunny is using, and every other professor in this course, not only Professor Sunny, he's using like such nomenclature that VA, I think, minus and VB minus, yeah. Okay, and then VB plus, VA plus, too much minuses and pluses for me. I never remember which one is which. Okay, sorry, okay. I propose my nomenclature. Pre means pre-impact, post will mean post-impact. Sounds good? Okay, and after the impact, we will have again this particle and this, and that time, of course, after the impact, this guy will have larger velocity than the other one, yes? So it will be post and VA post. Okay, so we have situation pre-impact, then they hit, and then we have the situation post-impact, yes? So by definition, coefficient of restitution is difference between velocities post-impact divided by difference in velocities pre-impact. So that will be VB post minus VA post divided by VA pre minus VB pre. This is definition. Okay, and this equation corresponds to the situation on the board. This equation corresponds to these two drawings. So if before the impact, this guy has velocity pointing this way, what shall I change in this equation? If I flip the velocity of the guy pre-impact, so I believe that VB pre, this would be plus here. Do you see? I have to switch the sign of this particular quantity. Do you see? Okay. However, if you remember this situation, that pre-impact A chases B, and then post-impact B is faster than A, this is the equation you should go for. And every other, this is how I remember that, yeah? And basically then, if, I don't know, this guy post-impact is pointing this way, just flip this sign, okay? That's all when it comes to lecture review. Any questions?
If you were to just solve using that initial equation, would you come out with negative velocities?
Would I come up with negative velocities?
B were going the opposite direction and you just use that the equation that's written on the board right now, you just come up with a negative velocity?
Then yes. However, as you know, I solve problems in magnitudes. Yes. So if I know for sure that pre-impact this die points this way, I'm going to go for this expression. I'm going to go for this expression if I know for sure. And usually we know what happens pre-impact, yeah? However, and then usually this is a great question actually, because usually what I assume post-impact is this situation. And then you will tell me what will happen if I obtain negative velocity at the end. That means that my guess was wrong. That means that this die was pointing this way. Yeah, I just assume that situation. I assume that situation always. And then if I receive positive values at the end, my guess was correct. Yeah, and if negative, then okay, it's going the other way. Okay, we're gonna do problem like that. Okay. Okay, any other question or example number 1? Okay, guys. As usually, please read and understand problem statement. All right, so what do we have in here? We have two bodies, yes, two particles. We know that this guy is at rest. This guy is at rest. We know that this guy has velocity 2 meters per second. We know their masses, and we know that in the second part, we will use information that there is a friction between this guy and the ground. Okay, and we also know coefficient of restitution between two bodies. So let's find speeds of the blocks immediately after the impact. Solution. Okay, we're gonna draw a situation pre-impact and post-impact. So let's do little dot, big dot, small dot, big dot, and of course this guy has velocity a pre, and this guy has little m, little mass. This guy has big mass, okay, and no velocity. And after, let's assume that this guy has velocity this way, and maybe this guy has velocity this way. We will see. VB post, VA post. Okay, we have our diagram. How about momentum equation? So during the impact, we usually go for momentum equation and coefficient of restitution equation. So we're gonna go for momentum equation. In the x direction, of course. My computer is not listening to me recently. Please start listening to me again. Okay. Yes, you're back? Okay, thank you. Okay. So this is our momentum in the x direction, and this direction is positive. And during impacts, momentum is preserved, okay? I mean unconstrained impact. In this case, momentum is preserved. Momentum preserved. Preserved. So we will have at the beginning mVA pre, and that's it. And at the end we'll have mVA post plus big M VB post. Okay, so how many equations do we have and how many unknowns? Aha, we do not know this thing. We don't know. We know what happens pre-impact, but we do not know what happens post-impact. Yes, so we have one equation and two unknowns. Okay, we need another equation. Which one? Which one? We are gonna go for coefficient of restitution. Yeah. So we're gonna go for restitution. So we have E equal to exactly what we wrote on the previous board. V post divided by delta V pre. So that will be VB post minus VA post divided by VA pre minus VB pre. Okay, if I remember correctly, this die was at rest. Yeah, so this is 0. And this die had 2 meters per second. Yeah, so this will be 2. All right. So we will end up with 2E is equal to VB post minus VA post. Great, we found our second equation. Okay, so let's just summarize our stuff. Yeah. So let's take this equation. I'm gonna copy it. I'm gonna copy it here. I'm also going to copy this equation. And this is with minus, okay. Okay, so let's plug in our values. Actually, you know what? Let's maybe also replace this guy. I like to have things arranged. So VB under VB, VA post under VA post, yeah. Okay, so now we will just have I believe 1. Yeah, it's 1, and this is equal to 0.5 VA post plus 2 VB post, and this will be 0.8, and this is equal to minus VA post plus VB post. Okay, just solve it. Here we have 2 equations, 2 unknowns. So we'll end up with VA post and VB post equal respectively minus 0.24 meters per second and 0.56 meters per second. Okay, so Will, this is the answer to your question. Yes, we have a negative value here. So let's see how our situation post-impact looks like. Hence, post-impact will have such situation. This die has 0.24 pointing this way, and this die has 0.56 pointing this way. That's it. That's how we solve these problems. Okay, end of part 1. Okay, guys, so in such situations, when you have two bodies impacting, just go for momentum equation and coefficient of restitution equation. Okay? Any questions? No questions? Okay, awesome. Part B? Yeah. No part B. Part 2. So they ask us, what did they ask us for? Aha, the distance block B travels after the impact. Yes. So we're gonna go for work energy method, yes? So we're gonna go for work energy. Okay, so we will have config A, configuration A, and configuration B. So let's have our ground in here and here. Let's say that our particle starts here with velocity 0.56. Let's mark our position here and here. And at the end, this die will be here. And they ask us for this distance. And just keep in mind that there is a friction. Okay, these are our two diagrams for work energy. Okay, T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. T1, V1, T2, V2, U12 non-conservative. Okay, and by the way, this velocity is 0. Velocity final is 0. So, I don't know, I'm gonna solve it. Yeah, I'm not gonna ask you for help here because everybody knows how to solve it. So T1 is 1/2 0.56 squared. Do we have springs in the system? No. Bodies change elevations? No. 0 here, 0 here. At the end, body stops, the kinetic energy is 0. But we have work of friction, yes? We have U12 of friction. So let's do quickly free body diagram. So we have mg, we have n, and we have friction. And this is our trajectory. This is our trajectory. So we will have integral from 0 to d of Tf ds, of course with a negative sign, and Tf is equal to mu k n because we are in kinetic friction, right? Kinetic friction regime. Okay, and we also know that mg minus n or minus mg plus n is equal to may. However, this die is 0 due to constraint. So from here we see that our n has to be equal to mg, and that means that our mu k mg is equal to tf. Okay, so we have minus integral from 0 to d mu k mg ds. This is constant. And we'll end up with minus mu k mg d. Just a reminder how to do a work energy method. Okay, next step, plug everything back in into our original equation. I think I have space here. I can do it here. So we will end up with 1/2 m 0.56 square minus mu k mg d equals to 0. Okay, one equation, one unknown. D is equal to 0.56 squared divided by 2 mu k g, plug in values, and obtain that d is approximately 0.04 meter. Questions? Okay, so second part was a reminder. First part was answer to Will's question from like 10 minutes ago. Okay, guys, in case there are no questions, we can do example number 2. Okay. So as usually, please familiarize yourself with the problem statement before we start our solution. Okay. So we have a particle, we have a laptop that we will model as a particle. We just drop it on the floor and it rebounces off of the floor, yes? And they ask us to find impulse acting on the particle and average acceleration during the impact. I have nothing else to say. So let's look at part 1 of that problem, which is falling down, the fall down, free fall of the laptop. Okay, so let's draw our ground in here, and also here. So that will be configuration A. This will be config B. We have our laptop placed here. We will model it as a particle. This distance is 1 meter. And it has mass m and velocity initial 0. And at the end, our laptop will unfortunately hit the ground with some velocity, v pre-impact. But let's save some ink and let's call it v pre. Okay. That's it. We're gonna go for work energy. I think nobody has any objections here. T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. And these 5 guys, and now these 5 guys. T1, V1, T2, V2, U12 non-conservative. Okay. Are there any more candies in the basket? No. Yes. So I wanted to ask somebody to help me for a candy. But you already received like 2 or 3. Yeah. So okay. System starts from rest. Yes, it is. Yes, it does. 0 here. System has velocity at the end. Yes. So it will be 1/2 mv pre squared. Yeah. No springs in the system, but I believe that something changes elevation here, yes? So let's put our datum here. I put it here. You can put it wherever you want. I'm gonna put it here. This is our datum. So at the end, our particle is aligned with the datum. That's probably not possible. Our elevation of our particle is at elevation of the datum. So 0 here. And before we have mg times 1. And there is no energy dissipated in the system. So we will end up with 1/2 mv pre squared is equal to sorry, minus MGA. The other way around. This one will be here, and this is equal to MGH. Yes. So mass all of a sudden does not matter, and we end up with V3 equal to 2GH square root. Plug in values and obtain that V3 is equal to approximately 4.429 meters per second. Okay, so we found situation pre-impact. Now I would like to focus on what's happening after the impact, okay? And we will leave the impact for the dessert, okay? So now let's see what will happen after the bounce, okay? So let's do part 2. After the impact. So we will have such situation. We will have configuration A here, config A, and config B. So we have again our ground. And what do we have after the impact? Right after the impact, I think that our particle is here, and it has velocity pointing upwards. Yeah, it would be V post impact, right? And then at the end, it will be at some elevation with velocity final equals to 0. Yeah, it will stop at some point. And I think that told us what is this elevation. Let me scroll up the board because I think they told us. Yep, here. Only 5 centimeters. That's interesting. So initial height is 5 centimeters. So this is 0.05. Okay. T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. Yeah. That routine is becoming a little bit boring. Yes, a little bit. Yeah. Sorry, guys. We have to do it anyway. But let's do it quickly then. If it's a little bit boring, let's do it quickly, as we should do usually with boring things. Yeah. Let's like mark them out from our schedule. Pick. Okay. No dissipation of energy in that moment. It's 0 here. Velocity is 0 at the end. At the beginning, we have some velocity. Datum will be here, of course. So we have 0 energy at the beginning and some energy accumulated at the end. 0.05. Great. So that means that we will have 1/2 mv post square equal to mg 0.05. Again, m can be cancelled out from our equation, and v post is equal to 2g 0.05 square root. Grab your calculators and find that v post is approximately 0.990 meters per second. Okay, great. So we found velocity before the impact and after the impact, yes? Questions? Great. So now let's focus on the impact. Part 3. Impact. So we will have situation at instant Yeah. Please observe that when I speak about energy, I say configuration and configuration. Yes, because energy, and when I talk about momentum, I talk about instance and instance. Yes, because momentum is integral of over time. Yes, so when we talk about momentum, we don't care how much distance was covered. We just care how much time it took for the event to happen. Yes. In energy, we care about the distance covered by the particle. Yes. We don't care. We actually don't know how much time it takes for the particle to cover. Okay. So momentum is time related. Energy is displacement related. Okay. Instant t0 equals to 0 minus. Yeah. Because impact takes like very, very little time. Then we have instant. Then we have actually not things like t that belongs from t0 to tf, and then we'll have instant. What these guys are doing here? Instant tf equal to 0 plus. So 0 minus means a very, 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 very small number, but negative. Yeah, and t0 plus means very, 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 very small number, but a little bit positive. Okay. Okay. So let's do pre-impact and post-impact. Let's draw our ground as well, again, here. Copy, paste, yeah. And we have our particle here, I believe, and we have mv pre, yeah. And by the way, we found that v pre, yeah. V pre-impact was, if I remember correctly, 4.429. Yeah, 29. Yeah, we found that v pre, yeah. So that was all the point of part number 1 of this problem, yeah, to find that velocity. Okay. Now we also know what happens after the impact, yeah, because we have particle here, but it is pointing this way right now. Yes, we have m v post, yes, and that v post we found in part number 2 of the problem. It was 0.99, I believe, yeah. So that was whole point of part number 2. Yes. Okay, and now let's see our impulse diagram. So we have our particle here, and what forces act on our particle? We have mg and we have n. Yeah, the reaction force between the particle and the ground. By the way, mg can be neglected when it comes to impacts. Neglect mg. Okay, we are only going to take care of n. Let's not forget about our integral t0 to tf dt. Okay, I think that's it. Yeah, we are done with our momentum diagrams. Yes, so let's write momentum equation. Momentum equation. Let's say along the y direction, and this direction will be positive, okay? So we will have at the beginning mv3, but it will be with a minus, yes? Because it is pointing downwards, so minus here. Then only n is acting on our particle, yes? Because we're gonna neglect mg. So we will have integral from t0 to tf of n dt. And that will be with a plus. And we will end up with m v post. Okay. What did they ask us for, by the way? Find impulse. Aha. So just find this thing. Just find this thing. Yeah. So our impulse. Let's save some ink. IMP. Okay. Imp is equal to m v post plus v pre. So IMP is equal to 2.75, 4.429 plus 0.99. Oops. Grab your calculators if you want to, and obtain that IMP is equal to 14.902 newtons times second. This is the answer. Okay, but they ask us to find one more thing. Yeah. Before we find it, any questions to what happened on the board? Yeah. Okay, so now let's see what they want us to find. Average acceleration during the impact. Okay, so let's now find AVG. Okay. Okay, so what was that definition of average acceleration? Aha, I just have some notes I wrote to myself yesterday. So I believe that we always can write that F equals to ma, yeah, and in our case F is n, yeah, it's that normal force, and if we integrate it over time, let's say from t0 to t final, dt here and dt here. So this is our impulse, yes? So our IMP will be equal to this integral, but we can replace it with, so this guy is a function of time. Yeah, it is not constant value, yes? But we can replace it actually with a expression with this constant value. And that expression is following. M A average times delta t. Okay, where delta t is obviously the t final minus t0. So we can replace that integral with this expression. Okay, I think we know everything to find A average. A average is equal to IMP divided by m divided by delta t. So let's use the value we found in previous part. So that would be 14.902. Mass we know, 2.75. And I believe that they told us that delta t is 10 to minus 3. Yeah? If I scroll up the word aha, yeah, we can see that the contact lasts 10 to minus 3 seconds. Let's plug it in. 10 to minus 3. Grab your calculators and obtain triumphantly that this is approximately 5.419 meters per second square. Some of you might think that this is the answer. It's not the answer because they told us to express this one in terms of g. So the actual answer is average is equal to 552.4 G. This is the answer. I would accept two answers, to be honest. Sure. So you must. I just skipped one step, Jason. So in order to obtain here, I took AVG. Oh, sorry, guys. Is equal to 5419 divided by 981 G, because G is 981, yeah. And if you plug this into your calculator, you will obtain this number. Finito. We're done. We're done with discussion. Yeah. Okay. Any other question? Yeah. Okay. So don't party too much during Halloween, and happy Halloween. Bye.